In this video we will tackle a two-stage epicyclic gear train.
The goal of this video is to compute rotational speed and direction of rotation of planet carrier labeled ARM2.
In the epicyclic gear train shown, gear N1 rotates at 1000 revolutions per minute in the clockwise direction when the gear train is viewed from the left. And annular gear N4 is fixed. Find the rotational speed and direction of rotation of ARM2.
So here we have two inputs and two constraints.
Using these inputs and constraints, we have to compute omega ARM2.
Note: while all other parameters are explicitly mentioned in the problem statement, the two constraints shown here are to be inferred from the diagram.
Stage 1 is the simple epicyclic gear train on the left, shown in green.
Like any simple epicyclic, it has 2 degrees of freedom. Stage 2 is the simple epicyclic gear train on the right, shown in blue. It also has 2 degrees of freedom. Time to take a closer look at the gear train.
Gear N1 is the sun gear of stage 1. It meshes externally with planet gear N3. It is input number 1. It rotates at 1000 RPM clockwise when the gear train is viewed from the left. Sun gear N2 of stage 2 is rigidly bolted to this gear, forcing the two to have same RPM and same direction of rotation.
Gear N3 is the planet gear of stage 1. It meshes externally with gear N1 and it also meshes internally with annular gear N4. It is carried by ARM1.
Gear N4 is the annular gear of stage 1. It meshes internally with gear N3. It is one of the two inputs. Gear N4 is forced to not rotate and is held stationary at 0 RPM. ARM1 is the planet carrier of stage 1. It carries the planet gear N3. Gear N5 from stage 2 gets welded to ARM1. Doing so forces gear N5 to rotate at whatever speed the ARM1 finds itself rotating at. Stage 1 is done. Now we look at stage 2, starting with gear N5.
Gear N5 is the ring gear of stage 2. It meshes internally with gear N6. As mentioned before, it is welded to ARM1 from stage 1, thereby forcing it to have the same rotational speed and the direction of rotation of the ARM1.
Gear N2 is the sun gear of stage 2. It meshes externally with gear N6. It is locked, welded to gear N1 from stage 1, thereby forcing it to turn at the same speed the gear N1 turns at.
Gear N6 is the planet gear of stage 2. It meshes externally with gear N2. And it meshes internally with gear N5. It is carried by ARM2.
ARM2 is the planet carrier of stage 2. It carries planet gear N6.
Our ultimate goal is to compute the rotational speed and the direction of rotation of this stage 2 member.
Animation showing how the two stages come together. 3D animation shows how the two simple epicyclics are constrained together to move as one mechanism.
Here we see ARM1 and gear N5 constrained to rotate with same speed and have the same direction of rotation. Now we are seeing constraint number 2 in action. Because of this constraint, gears N1 and N2 will have same speed and same direction of rotation.
Ultimate goal for us is to compute omega ARM2.
For that we shall have to first compute omega ARM1.
And we have the ARM1. So let's put the labels next to the gears. N1 is 20 teeth. N3 is 30 teeth. N4 is 80 teeth. And of course we have the ARM1. So we have two inputs. This is omega N1. We are told that this is 1000 RPM. clockwise. And we're also told that omega n4 is 0 RPM. Next step, we construct a table. Okay, first column, just simply list all the gears. So we have N1, then we have N3, next we have N4, and finally we have arm1. So we have the sun gear, the planet gear, the ring gear, and arm1. So this is column 1, super easy to do. We move on to column 2. Now what you have to do is lock everything together, and by that what I mean is no meshing of gears is allowed, no meshing of gears is allowed. And now if you were to give it a turn, the entire assembly will rotate with the same rotational speed, meaning gear N1 will rotate at x RPM, N3 will also rotate at x RPM, N4 will also rotate at x RPM, and surely arm1 will also rotate at x RPM. Moving on to column 3. This is where some heavy lifting takes place. Okay, column 3. So this is where we turn or transform our epicyclic gear train into an ordinary gear train. And the way we do that is we lock the arm, i.e. we prevent the arm from rotating. So arm 1 gets 0 RPM. So when that happens, we are left with a simple ordinary gear train where we have sun gear N1 driving planet N3, no longer a planet because the axis is now fixed in place. And we have N4, annular gear. So if N1 rotates clockwise, N3 will rotate anti-clockwise, and N4 will also rotate anti-clockwise. Now, as we said earlier, that we are looking at the gear train from the left. As we said earlier, that we are looking at the gear train from the left, and we're gonna consider clockwise rotations as positive. Okay, so now that we have this simple gear train to work with, let's give N1 a certain number of RPMs, let's say Y RPM. So if N1 rotates at Y RPM in the clockwise direction, N3 will rotate in the counterclockwise direction. But what would be the magnitude? And the magnitude would be that we would take the rotational speed of N1, which is Y, and we multiply it with a fraction where the numerator is the number of teeth on N1, which is 20 teeth, divided by the denominator, and the denominator will be the number of teeth on N3, which is 30 teeth, and we stick a minus sign next to it to indicate that the direction of rotation of N3 will be opposite from that of N1. Moving on to N4, we take the rotational speed of N3, which is this. So we take that minus 2 over 3y, and we multiply it with a fraction where the numerator is the number of teeth on N3, which is 30 teeth, and the denominator is the number of teeth on N4, which is 80 teeth. And we stick a plus sign next to it because N3 and N4 both rotate in the same direction. Okay, we are done with column 3. Column 4. Column 4 is very easy to do, very easy to populate. All we do is we take whatever we have in column 2 and add it to whatever we have in column 3. So for gear N1, we add x to y. In gear 3, we have x in column 2. We add it to whatever we have in column 3, which is minus 2 over 3y. Minus 2 over 3y. For gear N4, we have x in column 2. We add it to whatever we have in column 3. Now, if you do some algebraic simplification, you should end up with minus 1 over 4y. Minus 1 over 4y. And finally, for arm 1, we have x in column 2, and we have 0 in column 3. Column 4 is done. We move on to column 5. For each row, in each cell, just print equal sign. It will become obvious pretty soon. We move on to column 6. So first row is for column N1. Just write omega N1. That is the rotational speed of N1. Second row is for planet gear N3. Just write omega N3. Third row is for the ring gear N4. We write omega N4. Last row is for arm 1. We write omega arm 1. And this completes our table. We have now fully populated. We have now fully populated the table for stage 1. So let me write it here. Table for stage 1. After completing the table for stage 1, cover the columns 1, 2, and 3. We don't need them anymore. And now just look at the columns 4, 5, and 6. You will notice that you are actually looking at 4 equations. Sorry, let me use a different color. So let's highlight columns 4, 5, and 6. So you'll find yourself looking at 4 equations. So I've isolated the equations and brought them down here. And now we just have to solve for x and y. So these are the 4 equations we got from table from stage 1. So if we look at them, we realize that if we knew the values of x and y, we could figure out the rotational speeds of any of the elements in stage 1. So our next job or task is to solve for x and y. We do that by noting that we already know what omega n1 is. So we replace that with 1000 RPM. And we also know that omega n4 is 0 RPM. So when we do that, we get two equations with two unknowns. So first one is x plus y. This is this one. And that is equal to 1000. And the second equation is the one for omega n4. And that one says that x minus 1/4y is 0. If we solve these two linear simultaneous equations, you will find that x comes out to be 200 and y comes out to be 800. Now that we know the values of x and y, we can go back to the equations and compute the rotational speeds of any of the members. Well, two of them we already knew what they were. They were the two inputs for our simple epicyclic called stage 1. We are particularly interested in omega arm 1 because this rotational speed becomes one of the inputs for the second stage. So let's find out what omega r1 computes to. Omega arm 1 is actually simply equal to x. X is equal to 200. Therefore, we have 200 RPM. Since the answer is positive, this means that we are looking at this rotational speed where the direction of rotation is clockwise, because that is what we said right at the beginning, that when the gate train is viewed from the left, any rotations in the clockwise directions will be considered positive. And since we are getting a positive answer, omega arm 1 will be rotating at 200 RPM clockwise.
Results from stage 1. In response to the two inputs omega n1 and omega n4, the planet carrier, arm 1, responds by rotating at 200 RPM in the clockwise direction.
So now we are ready to do stage 2 and solve it. So when I say we solve it, what I mean is that stage 2, just like stage 1, is a simple epicyclic gate train. We will need two inputs to get the output. And in this case, this is the output we are looking for. So draw the diagram, mark the inputs. One is omega n5. Remember, it's connected to the arm 1 from stage 1. And now that we have solved arm 1 from stage 1, we know that this is 200 RPM. Clockwise. Similarly, we know that omega n2 is 1000 RPM because it is directly connected to directly connected to gate n1 from stage 1. Clockwise. And omega arm 2 is the ultimate goal. We need to find omega arm 2. So very quickly we will note down the number of teeth. We will need these for column 3. So N2 is 25 teeth. N6 is 35 teeth. And N5 is 95 teeth. Now you will notice that I've already drawn out the column, the table. it will have 6 columns as before, and the number of rows is exactly equal to the number of elements we have in the drivetrain. So we have 1, 2, 3, 4. 1, 2, 3, 4 rows. The columns that are super easy to do, I've already filled them out. Column 1, column 5, and column 6. Column 2 is also super easy. You will find yourself printing X in all the cells. Column 3 is where the action happens. So column 3 is where we temporarily transform our epicyclic gear train into an ordinary gear train. We do that by locking the arm. Once we do that, we are left with a simple ordinary gear train with just 3 gears. N2 driving N6, and N6 in turn drives N5. So first thing we do is we put a 0 for arm 2. Next, we give N2 an unknown number of rotations per minute, or whatever the units are. So let's say we give it y RPM. Now N6 is driven by N2. If N2 drives at y RPM, N6 rotational speed will be, we take the rotational speed of N2 and multiply it with a fraction. Numerator will be the number of teeth of N2. N2 is 25. Denominator will be the number of teeth on N6. N6 is 35 teeth. And because it's external meshing between N2 and N6, if N2 rotates clockwise, N6 will rotate anti-clockwise. So if this is plus y, the rotational speed of N6 will be counterclockwise. So I'll have to put a minus sign here. Moving on to N5. The meshing between N5 and N6 is internal because N5 is an annular gear. So what we do is, as before, we take the rotational speed of N6, which is minus 25 over 35y, and we multiply it with a fraction where the numerator is the number of teeth on N6, which is 35. Denominator will be the number of teeth on N5, which is 95. And this time there will be no sign change because both N5 and N6 will be rotating in the same direction, clockwise or anti-clockwise. Column 3 is done. Column 4, as mentioned before, is just adding whatever you have in column 2 to whatever you have in column 3. So here we get X from column 2 plus Y from column 3. Here we get X plus whatever we have here, and if you simplify it, you should get minus 5 over 7 y. Here we have X from column 2. We add it to this quantity, and again, if you simplify it, you should get minus 5 over 19 y. And here we have X from column 2 plus 0. So I'll leave that out because X plus 0 is just X. And yeah, so as before, now we are ready to extract the equations. We do the same thing. We hide columns 1, 2, and 3. We don't need them anymore. And we find ourselves looking at 4 equations where the X and Y are unknown. So we bring these 4 equations down. Next, we replace what we know. So we know that omega N2 is 1000. And we know that omega N5 is 200. This is coming from this one. Once again, remember it was attached to arm 1 of stage 1, and we had just calculated that arm 1 was rotating at 200 RPM. So this becomes an input to stage 2. And also gear 1 was directly connected to gear 2, and therefore they will also rotate at the same RPM. Once we do that, we get two equations with two unknowns, which are x plus y. And so this is the equation number 1. This is equal to 1000. And then we have the equation for gear N5, which is x minus 5 over 19. Y is equal to 200. Once again, two linear equations that can be solved simultaneously. And if you solve them, so let's box them first. So we say solve. You could use any number of methods to solve these. I usually use Desmos. I just plot these two straight lines and get the intersection point. So you would get x to be equal to 1100 over 3, or 366 2 by 3 revolutions per minute. And y would come out to be 1900 over 3, or 633 and 1/3 revolutions per minute. So once we know x and y, we go back to our table, and since we are interested in omega arm 2, that is the final output of our epicyclic gear train, we notice that omega arm 2 is simply equal to x. So therefore omega arm 2 is equal to x. Now x is 1100 over 3, 1100 over 3 RPM, and it's clockwise. Why? Because there's a plus sign next to it, and we said in the beginning that if we view the diagram from the left, all rotations that are clockwise we will consider them as positive. So since the answer is positive, we know that the arm 2 is rotating at 1100 over 3 RPM in the clockwise direction. And this is our final answer. So let's draw a nice box around it. So folks, this concludes our video on the solution of a two-stage epicyclic gear train. Thank you for watching.